Hello everyone, so I will show you the results of some joint work with Adrien Guinet, Ninon Hérol and me, Marion. Ninon is also doing a PhD with the University of Versailles, and I'm also affiliated with GreHack in Nancy. And the work I'm going to present you today, a little warning. I've been warned yesterday that I had to give this talk because my co-author made the best joke you can do to your co-author, having a real good reason not to be able to attend the conference, just the eve of the event. So I've been warned yesterday, so please be patient. I didn't do the slides by myself, and neither the demo, so I'll try to do my best then. Okay, so what is this talk about? We'll show you a little bit why we are trying to tell you the story of these two little candy bears. One is called arithmetic, and the second one is called Boolean. And in the real world, they get on well with each other quite well. And in some kind of theoretical world, they don't have any tools to get on with each other well. And what we are trying to do is to show that we can do things so that we can manipulate them in some world, in computer world. Okay, so a few years ago, there were people, colleagues in Quark's lab, trying to reverse iMessage protocol, and they stumbled upon this piece of code. So when you see that, okay, you're trying to find an equivalent a little bit more readable, and what is the readable function? It's that. So you see there is a lot of arithmetic operations mixed with Boolean operations. And either you are working in cryptography and you are wondering if this is some part of the cryptographic algorithm, or you are working with optimizations because you are interested in compilation, and you say, okay, easy, the compilator will simplify that. And in fact, it's neither cryptography nor simplification. It's something we don't know. So Adrien also tried some kind of source-to-source compiler, and in fact, nothing worked. And meanwhile, the colleagues, they went on with brute force, and it worked. But after they brute forced, we still had this question, why compilers are failing to simplify that? Because it can be simplified. So let's take a closer look to one part of this function. We can see that there are arithmetic operations, there are Boolean operations, and they are closely intertwined with each other. So the optimized version, the compiler output is this one. So you still have arithmetic operations and Boolean operations. And the one thing we do with Arybo is just outputting this simplified expression. So at the end, you should be able to get a XOR operation. And the compiler is not able to output that. So our talk is about how getting from this big thing to this small one. And we thought that it could interest a lot of reversers to get this type of simplifications. Okay, so our goal is to simplify expressions with mixed operators. So it's called mixed Boolean arithmetic expressions. So you will find MBA. So in the context of obfuscation, it's called MBA. You can meet this type of expression elsewhere, of course. They are not typically called this way. But maybe the more it will be known, the more people will call them MBA. So there are some typical examples, especially in big hacks, for example. So this expression is equivalent to XOR, but this one is also equivalent to XOR. We have at Quark's lab various related projects. The one is measuring and reducing the complexity, in some sense of complexity, of MBA expression. And we presented a result at International Workshop on Software Protection this year. Ninon Erol, so one of my co-authors, she published a tool on Quarks Lab's GitHub to simplify MBA expression by pattern matching, in some sense of simplification, in the blue sense of simplification, the one corresponding to the blue sense of complexity. And we are also using MBA passes in Quarks Lab Obfuscator in Luna. And there is this current work on how to use Arybo, and Arybo is implementing a strategy called bit blasting. Okay, so once you know that compilers aren't able to simplify these expressions, you are wondering what is the real reason, what is the intrinsic reason why it's not possible. And you are wondering if there are already some tools who would be able to do that. The first one is, okay, say there should be maybe computer algebra system able to do that. And these systems are implementing operations and rules on symbolic sets and variables. So this might work. So it handles operation at the symbolic level, and it usually provides several simplified functions. Maybe you remember in your early years trying to simplify polynomials, for example, try to simplify derivative functions, etc. The problem is that they usually do not easily handle the mixing of operations from different sets. Usually we're working with polynomials, meaning plus or and multiply in some sets. But you are not mixing plus with or, with and, with XOR, etc. And most of them does not support bitwise operators. So you don't have the right to mix operations. And they are the type of usual tools you encountered maybe in your life. The second strategy you can think about is constraint solvers. So these tools, they decide whether a system of equations is satisfiable or not, and it computes a solution if it's available. And well, I'm not really in SMT solvers, so I don't really know what's happening inside, but there's some kind of magic which makes them efficient. The problem is that they prove that an expression is equivalent to another one, but they do not output a simpler expression in our expected sense. So we cannot use them straightforwardly. And you have some kind of usual suspects too. I guess you met Z3, for example. So these two types of already existing tools, we cannot use them. So, as I told you, Ninon was working on pattern matching. The fact is that when you're writing mixed Boolean arithmetic expressions, you are using some kind of equivalencies. So you have a simpler expression, as I showed you, is XOR, and then you get some kind of mixed Boolean expression. So if you can write it one way, why not writing it the other way? So that's the basics of this strategy. What's interesting in this strategy is that it works at the word level. The second point is that it supports any arbitrary operation, of course, because you just need to have some kind of symbolic operator and know what it's doing by writing it. So there is no additional cost due to the support of arithmetic operators over Boolean ones. In fact, all operators in some way are equivalent, so it's completely operator agnostic. The problem is, of course, it will not simplify unknown patterns. You can do magic, but not miracles. And associativity magnifies the algorithm complexity. And there are issues with optimized inline expressions, like constant folding, which complexifies the process. And as of the tools, as I told you, Ninon implemented it in the tool called SPAM. And then you have this last strategy we implemented in Arybo, which is describing what happens in the bit level using a bit vector. This allows to compute the Boolean formula of each bit of a given n-bit expression. So the strategy is, you know that at the end, every operation can be described at the bit level. So as it's the only level where you're sure of what's happening, then you will take all your operation and put it in the Boolean world. So this is the example. For example, you have your 4-bit variable, and you want to compute the addition with 1, the arithmetic addition. And in the Boolean world, it gives this formula for every bit. So of course, as it's at the bit level, you have a fine-grained understanding of what's happening. And one of the magic of this representation is it's canonical, which means that every expression that at the end are the same written this way, you are sure they are equivalent. They do exactly the same thing. It's obviously not pattern-based, and it's an interesting tool for other topics like cryptography or optimization. I mean, it's not only needed for that. The problem is that, of course, when you go to the bit level, if you want the word level expression, you need a process. And you need this process to go back to the word level. And in fact, we don't know if it's always possible, in fact. And the second problem is arithmetic operations at the bit level generate big expressions because you have bit dependencies and you have non-linearity added, for example, with addition, and of course with multiplications. And it's hard to identify complex expressions, and it might even not be possible, as I told you. And this is a strategy we implemented in Arybo. Okay, so now we are going to the tool. What is Arybo? These little candy bears. So Arybo is not your regular candy. It's a Python 2 and 3 library to manipulate mixed Boolean arithmetic expressions. And the expressions are bit blasted, but they can also be processed at the bit level, at the word level. Sorry. The fact is, the later you process at the bit level, the more kind of simplification at the word level you can put before, because the bit level is quite costly. So you try to avoid to pay too much too early. Boolean expressions are represented under the algebraic normal form. It's a choice we made. One of the advantages is that it's easier for me to understand, which is one advantage. It's a canonical form, and it's only using XOR and AND. The XOR as a plus modulo 2, and the AND as a multiplication modulo 2. There is a C++ library called libpetanque. Because you're handling Boolean operations to manipulate Boolean expressions, and it's under a BSD license. Okay, so in libpetanque, what do we do? It's a C++ protein library to handle Boolean expressions with their abstract syntax tree. It generates a algebraic normal form canonical expression from any arbitrary AST, and it's designed for performance and small memory footprint. And there are Python binding thanks to PyBind 11, and the binding is called petanque, of course. And why do we do that? Because there are no efficient equivalent library, and we can use it as a sandbox to test several things, for example in crypto. And you can try it by yourself. And as there is a Wi-Fi in the amphitheater, you can even try it now live. Okay, a little demo then. If it works. Yes. So here is a little notebook. Okay, what do I say here? I'm using mixed Boolean arithmetic expressions. I'm going to use 4-bit expression using 4-bit variables. I have a variable x, I have a variable y, and if I do this, you have your two vectors, your two symbolic vectors. Okay, so you are just asking to get two 4-bit symbolic vectors. Here, for example, you might want to get a vector from a constant. You know that 7 is a 4-bit constant, and you want it to be written in Arybo so that you can use it. So here is the vector. So here is the least significant bit, and here is the most significant bit. You have to read it the other way around. Okay. And here you have these different Boolean operations that are supported. So if you want to do the XOR of these two variables, the AND of two variables, or the OR of these two variables, and you want to do it symbolically, what do you get? So you see here that the XOR is the OR modulo 2 at the bit level. You see that the AND is the multiplication modulo 2 at the bit level. And you see here that the OR is some kind of mix between addition and multiplication. All right. And here you have some more examples with constants. If it works, yes. So here you have the simplification of this expression. And the only remaining variable is the last bit. And you can do the same with AND. And here you see that the only remaining variable is the least significant bit. Okay. So next we go to the arithmetic operations. For addition and subtraction, we describe a 1-bit carry logical adder or subtractor, and we do this for each bit. And we optimize when one of the operand is a non-constant. For multiplication, we do it the old way, with like with additions. And the division by a non-constant, we transform a division by a multiplication. And the algorithm is taken from Hacker's Delight. So let's see. Let's see the next slide. Yes. It seems like it's prepared. Okay. So here is the addition. So here you can see the type of dependency I told you about. Here, the third bit is depending on the first and the second bit. The first is here, and the second bit. And the last bit is dependent on the first, the second, and the third bit. And all these multiplications are nonlinearity. There are a few more things you can do, like evaluating this operation on a value for x. So here you have the evaluation, and you ask for the output, and it says it is 5. So it's a nice tool to say that 4 plus 1 is 5. You are happy with that. Okay. But you can do more symbolic things, like adding x plus y. And here you feel why additions, arithmetic operations are adding a lot of complexity. Here you're just two 4-bit variables, and you already have something that is hardly readable on the screen. And you're not usually working with 4-bit variables. So here, 1 plus 5 is 6. Woohoo. Right. Okay, In fact, I ended the demo a little early. There are a few fancy things you might want to do. And it's the beginning of what we call identification. You have this operation, you have your two variables, and you have some kind of operation mixing Boolean and arithmetic operators with constants, and you want to know if there is something you can take out from this expression. Okay, so this is the print. It says the operation is equal to this vector. And as you can see, this vector, it hasn't any variable, so it should be a constant. So you are asking, what is the constant value for this result? And the constant value in hexa is this one. So you've been able to simplify with Arybo this expression. It is the same if you are trying to use this one. You can see that the resulting vector is just a constant, and the constant is 7. Okay. So, what do we want to do with identification? It's just providing Arybo with a vector with variables and constant, and we want it to output these kind of things. Okay. And it works with this one, it works with this one, it works with this one. Well, the thing is that with the actual version of Arybo you can install readily on GitHub, you don't have the identify function. You have to use the feature expression branch. And 1 hour ago I didn't manage to really make it work, so I won't make the demo. But to give you a flavor, we will come back to the original example I gave you at the beginning of this talk, which is this obfuscated function. If you remember, it was a XOR. So, will Arybo manage to prove this is a XOR? Okay. So, you compute the function, and at the end, Arybo says it's this function. I say, ooh, it's much simpler. So, what can we say about it? So what we are asking Arybo now is to do some kind of a vectorial decomposition. So it will say there is a vector and there is a constant that we add to this vector. And we'll ask him to print this decomposition, and as we see that there are no nonlinear parts, of course there is just a variable and a constant. So we have some variable, XOR a constant. Right. So the decomposition says there is no nonlinear part. The nonlinear part is 0. It also says that there is a matrix times the vector x, and this matrix, you see its identity, so the vector x is taken as a whole, and then you have the constant part, and the constant is this one. And as you see there is a constant, you know there is this function getting the constant from a vector, and you are asking the value of this constant, and the constant is 5c. So that's how we managed to reverse, to simplify the obfuscated function.
5 minutes left.
Okay, thanks. So now I will rush until the end of the slide. Okay. That's the part I'm not completely at ease with, so I will try to do it quickly, and if you have questions, then we will phone Adrien afterwards. Okay, there is a need to represent the fact that you've identified a simpler function. You have obfuscated an MBA obfuscated function, and then you need to put it somewhere, not to take all this complicated function with you. And there are plenty of existing intermediate representation in the world, because every time someone is making a tool, it decides that it's better to have its own. And there is potential heavy dependency introduced, so we decided that we need our own one, of course. Like everyone, because everyone is right. This is a little failure from an engineering point of view, so we are trying to improve the situation. We'll come back to this in the conclusion. So, that's exactly the place where you feel a little bit, you feel some kind of unease, because that's supposed to be a joke, and it's not mine, so I don't understand it. But never mind. So there are other functionalities. One interesting one is that Arybo is manipulating algebraic normal form, and there are several occasions where you can encounter in the nature Boolean functions expressed by the value table. For example, S boxes in cryptography, they give you, for each input, they give you the corresponding output, and it's a function. You just have the value table. And if you want to compute the algebraic normal form from the value table, you have a known transform called the Möbius transform, which allows to do that. So we implemented it in Arybo. Okay, so I won't do the demo because I don't know how it works, in fact. I know how it works, but I don't know how to call it. And then we made some interesting things with Triton. I won't do any demo with that because Jonathan is in the room and he will make a rub session about it. So he will explain to you what is Triton and what he managed to do with it. So why, it's an interesting part of the story, why working with Triton at first, but because Jonathan was just in the adjacent room. So we decided to work with someone just there, so we can ask questions and get easily the answers. Okay, so what did we do? We had some obfuscated assembly code. Triton managed to de-obfuscate it. We put it in Arybo intermediate representation, which allows it to optimize it with LLVM. And at the end, we got a simpler binary code, instead of remaining with a Triton intermediate representation. So that's the idea of what we want to do with all the other tools. So this one is during the drum session. So we put lots of various pieces together. We worked at a basic block level, and as you've seen, bit blasting isn't necessary. So there, you see two different levels in Arybo: the place where there is an intermediate representation where you work at the word level, and if you need it, then you add bit blasting. And of course, not every expression, I say it again, not every expression can be identified once bit blasted. Okay, then what's coming next? You've seen that there is a big complexity added when you're manipulating arithmetic expressions. The thing is that arithmetic operators, they are intrinsically in some way symmetric, which means that all the bits of the same function have the same function in the operation, and this can be represented with symmetric functions. And if we are able to use symmetric functions, then the size of the algebraic normal form is greatly, greatly reduced. So we would like to do that, but it's not that easy. And then we would like to do automatic memoization, and it's not the part that I'm going to talk a lot, but it's some kind of reducing the size of the representation of X boxes. And then that's the great dream, managing to be at the center of everything. You take all the different intermediate representations, you put it in Arybo, and then you're able to to process it, to optimize it to the LLVM, and at the end you get binary code. And that's all. Thank you.